In this problem, we're taking a look at the number of births as a function of the number of actual years in the U.S. And we want to find a linear regression equation for this data. We'll let births be represented by B, years be represented by a Y. And so here is the graph of the equation. The equation itself is actually going to be births is equal to the initial value, which is, we'll just round that up to 4 to make it simple, plus 0.04 times the number of years. Okay, so there's our linear regression equation. Graph of the function, does it appear they fit the data points well? The graph fits the data points well, and it does. It doesn't look too terribly bad. It looks like there's a little bit of a trend here. It almost looks a little bit curved, like it's dropping towards the end. And it looks like it started off high and kind of dropped and came back up and dropped again. So maybe it's not the best possible model, but it's not bad. Compare your answer in B to the r squared, the value of r squared. Does it say the line fits well? Comment. Well, it's r squared is equal to about 0.81, which is not bad. That's about an 81% quality fit, so to speak. And we want to identify the rate of change as well, so that's 0.04. If you want to put it over 1, that might help. 0.04, this is change in output over change in input. Output is the million births. Now, it's in millions, so these numbers are 4.06 million. So that would be per 1 year. Now, alternatively, if you want to multiply this by millions, because it's 0.04 multiples of a million, you'd actually get, let's see, you'd get 4... I think that's exactly what you'd get there. So 40,000 births per year, if you want to think about it like that. But we'll treat it this way just to keep the numbers smaller to deal with. According to the model, in what year can we expect 5 million births? Okay, so we want the number of births to be 5 million, so we'll put in 5. Now this is already in millions because these are already in millions. And we want to know in what year, since this is trending upwards, will we eventually reach 5. Okay, so 5 million equals 4 plus 0.4y. And so we subtract 4 from both sides. We get 1 equals 0.04y. Divide by 0.04. And we get y equals, let's try this out, 1 divided by 0.04, which is equal to 25. So we would expect that in 25 years after 2000, so this would be 2025, the number of millions of births per year would reach 5 million births. That's a big deal, actually, because that's a lot of people being born each year, and it's only going up. So what does that mean for world population and the likelihood of plague and things like that? Scary things to think about. Find the horizontal intercept. What is its real world meaning? Okay, so the horizontal intercept, if we recall, is where the points cross the horizontal axis. And the only thing we know about each of these ordered pairs is that the output value is 0. The output is totally zeroed out. It's the input that's changing. So we want to set the output to 0. So, oh wow, when will it be 0 births? 4 plus 0.04y. Subtract 4 from both sides. We get negative 4 equals 0.04y. Divide by 0.04. And we get negative 100. So y is equal to negative 100. Well, that's weird. How do we get a negative value for the years? Well, positive values mean you're going this way. Negative values mean you're going this way. So 100 years before 2000, or 2000 minus 100, would put you in the year 1900. So it doesn't make sense to say that in the year 1900 there were 0 births per year. Probably not. But the mathematics tells us that if you were to graph this, well, the number of births in 2000 started at around 4. Notice that this number and this number are a little off, but that's part of modeling. And then it continues to rise. So really, mathematically, this line goes backwards in this direction, so it would have crossed the horizontal axis 100 years ago. So it's not a really practical significance, but that's what it would mean if we were to try to interpret it.